In this video, we're going to do a review of 2 by 2 determinants. So we are going to let A be the 2 by 2 matrix A1, A2, A3, A4, and we're going to let B be the 2 by 2 matrix B1, B2, B3, B4. Now, the definition of determinant for 2 by 2 determinants says that the determinant of A is going to be the product of the main diagonal minus the product of the other diagonal. And so the determinant of A is going to be A1 times A4 minus A2 times A3. Likewise, the determinant of B is going to be B1 times B4 minus B2 times B3. And the first thing that I want to do in this particular video is look at a theorem that you may remember from linear algebra, which is that the determinant of a product is equal to the product of the determinants. Now, this is true for all n by n matrices, but what I want to do is I actually want to prove this for the special case that A and B are both 2 by 2 matrices. And the reason why is that it turns out that if you're trying to prove this in the general case, you need to have a much more general definition of the determinant, and the computations get a lot worse. So what I want to do is I want to basically start my proof with, again, we're going to let A be this matrix, and B be this matrix. And we're going to actually compute the product matrix, and then we're going to compute the determinant of the product matrix. So when we look at the product A times B, we're looking at the matrix A1, A2, A3, A4 times the matrix B1, B2, B3, B4. And when we do the computation, we're going to have, of course, this row dotted with that column for our first entry. And so the 1, 1 entry in this 2 by 2 matrix is going to be A1, B1 plus A2 times B3. This entry over here is the top row dotted with the second column, and so we wind up getting A1 B2 plus A2 B4. The entry down here is this row dotted with this column, and so we wind up having A3 times B1 plus A4 times B3. And this final entry over here is this row dotted with the second column. And so this final entry is going to be A3 times B2 plus A4 times B4. Well, once we have AB computed, we can easily compute the determinant of A times B. The determinant of A times B is going to be that particular number times this number minus this number times this number. And so we're just going to write that product out right now with parentheses. So we're going to have A1 B1 plus A2 times B3 times A3 B2 plus A4 times B4 minus A1 times B2 plus A2 times B4 times A3 times B1 plus A4 times B3. Well, what we've now got is a bunch of algebra that we have to deal with. We have to actually distribute out this product, and then we're going to have to distribute out the second product. And when we do that second product, we want to put that minus sign in front of every one of the terms because it's multiplying that whole product. So our next step of algebra is going to be to multiply this particular term up here by both of these guys. So we're going to have a1b1 times a3b2 plus a1b1 times a4b4. And then we're going to have this term here multiplied with both of those guys. So we get a2b3 times a3b2 plus a2b3 times a4b4. And now we have to do this product here in the same way. And again, that minus sign is going to be in front of each and every one of the terms. So we're going to have minus a1b2 times both of these guys, a1b2 times a3b1 minus a1b2 times a4b3. And then we're going to have this guy times both of those guys, and that minus sign is going to be in front of both of them, so we will have minus a2b4 times a3b1 minus a2 times b4 times a4b3. Now when we start looking at this, we're going to notice that a couple of these things are going to go away. Up here we have an a1b1. Well, if we start looking for that, we wind up noticing that we also have an a1b1 a3b2 right here. In other words, here's the a1s, here's the b1s, here's the a3, here's the b2. So these two terms add to 0 and we'll just cross them out. Now, if we continue looking for this, we'll also notice that we have way over here an a2 a4, and we have an a2 a4, and we have a b3 b4, and we have a b3 b4. So these two terms are also going to add to 0. So we'll get rid of them as well. And so what does that mean that we're left with? Well, that means we're now left with this particular thing. We have an a1, and I'm going to actually write all of these terms with the a's first and the b's second. So we have, for this term here, we're going to have a1 a4 times b1 b4. And then for this term, we're going to have a2 a3 times b2 b3. And then for this term here, we're going to have minus a1 a4 b2 b3. And the last term that's left in our expression is that one, and we can rewrite that one as minus a2 a3 times b1 b4. And what I want to notice is that we now are set up to do some partial factoring. In particular, we have an a1 a4 in that term, and we have an a1 a4 in this term. And we have an a2 a3 in this term, and we have an a2 a3 in this term. So I'm going to gather those like terms, and then I'm going to factor them. So we have, at this point, a1 a4 b1 b4 minus a1 a4 b2 b3. And then we have a plus a2 a3 b2 b3 minus an a2 a3 times a b1 b4. And we're going to factor a1, a4 out of those two terms. And when we do, we're going to have a1, a4 times b1, b4 minus b2, b3. And we can factor an a2, a3 out of these two terms. And when we do that, we have an a2, a3 times a b2, b3 minus a b1, b4. Now, at this point, what I want to notice is that the things in parentheses are almost equal to each other, but the terms are in the wrong order. And so what I'm going to do is I'm actually going to factor out a -1 from this particular term. And what that means is that we will have, as our next step, a1, a4 times this stuff. And then I'm going to have that a2, a3, and I'm going to go ahead and factor that -1 explicitly out. And when I do, I'm going to actually have a minus b2, b3 plus a b1, b4. And at this point, I want to clean this thing up because I want to make it very easy to do a little bit more factoring. So this minus sign is going to come out here. And I'm going to swap the order here so that it looks just like the order over there. And when we do that, we're going to have a1, a4 times b1, b4 minus b2, b3 minus a2, a3 times b1, b4 minus b2, b3. And after we've got that, what we can then do is we can actually factor out this mess. And when we do that, we wind up getting a1, a4 minus a2, a3 times b1, b4 minus b2, b3. And the first thing just happens to be det A, and the second one just happens to be det B. And that's the end of this particular proof. Now, there are a couple of really important corollaries for this particular theorem that I want to actually go over. So, the first big corollary is this. If A is an invertible matrix, so if A is invertible, meaning A inverse exists, then the determinant of A is not going to be 0. And the proof is based on the fact that A times A inverse is equal to the identity matrix, and we're still in the world of 2 by 2 matrices, and the identity matrix looks like that. So the determinant of A times A inverse has to equal the determinant of this guy. And using our corollary, this side can be broken up to be determinant of A times determinant of A inverse, and the other side, this side here, we can compute that determinant explicitly. That determinant is 1 times 1 minus 0 times 0. In other words, that's equal to 1. So we've now got the determinant of A times the determinant of A inverse is equal to 1. And what I want to notice is that this means the determinant of A itself is 1 over whatever this number is, but that can never be equal to 0 because the only fraction that equals 0 is 0 over a number like 1, or 0 over any non-zero number. In other words, once we get down to this particular equation, we can actually conclude that the determinant of A and the determinant of A inverse, neither one of them can be 0, because if either one of them were equal to 0, then the product would be 0. Now, obviously, there's another thing that we have just proved here, and this is worth pointing out as well. This fact itself is an extremely important fact, so let's get that written down as a second corollary. And we're going to make this note. We have also proved a second fact, that if A is invertible, then the determinant of A and the determinant of A inverse are multiplicative inverses of each other. You can rewrite this fact here as the determinant of A inverse would also be 1 over the determinant of A. Now, it turns out that our corollary goes both ways, and I want to look at that as well. So let's look at one more corollary. To our big theorem. And this corollary is, if the determinant of A is not equal to 0, then A inverse exists. So what we're going to actually do for trying to prove this corollary is we're going to try to prove the contrapositive. So we prove the contrapositive. And the contrapositive of this theorem would say, if A is not invertible, in other words, A inverse does not exist, then the determinant of A is going to have to be equal to 0. Now, it turns out that A inverse does not exist means several things. In particular, it means that the row-reduced echelon form of the matrix A is not equal to the identity matrix. And since we're dealing with 2 by 2 matrices, it means that A does not row reduce down to the 2 by 2 identity. Now, there are only a handful of different things that the row reduced echelon form might look like. And so what this says is that the row reduced echelon form for A must look like one of the following matrices. Well, the first one is A itself could actually be the 0 matrix, and there's no row reduction. The second one is that A row reduces down to something that looks like a 1 upstairs, and then I don't know what's in that particular entry, but the bottom row is 2 zeros. And then the third case is that A row reduces down to something that looks like this. Because every 2 by 2 matrix is going to have a row reduced echelon form that looks like one of these 4 things. And the 0 matrix is the only one that is going to look like the 0 matrix in row reduced echelon form. Well, what I want to notice too is there's another thing. Row reduced echelon form has a very special property, and that is the following. So I also want to recall another thing from linear algebra, that the way you do row reduction is you're basically multiplying by elementary matrices, and the elementary matrices, by the way, are all known to be invertible. So if A row reduces to something like, well, if it row reduces to, I'm just going to call it matrix B, then there exists a sequence of invertible, they're called elementary matrices, that do the row operations, and it's such that do a row operation until you get down to the last of these row operations. That guy winds up being B. So what this says is that the determinant of B is equal to the determinant of, let me get my notation right. The determinant of all of these elementary matrices times A, and this is going to be the determinant of all of the elementary matrices. I should again get that notation right. So, and what I want to notice is that all of these numbers by our first corollary, since these guys are all invertible, this product is not 0. But if you look at the appropriate reduced row echelon forms for non-invertible matrices, we know what B looks like. B looks like either 0, 0, 0, 0, or B looks like 1 something 0, 0, or B looks like 0, 1, 0, 0, since we know that A inverse does not exist. And what I want to notice here is that the determinant of each one of these guys is equal to 0. And consequently, what we have now is a 0 on this side of that equation from the determinant of B is equal to some non-zero number times the determinant of A. Well, so since we now have 0 is equal to a non-zero number times the determinant of A, that forces 0 to be equal to the determinant of A. And consequently, what we've now proven is if A is not invertible, then the determinant of A is equal to 0. And if you put this together with our previous corollary, we have now proved that A is invertible, so A inverse exists, if and only if the determinant of a matrix is not actually equal to 0. Now, from a modern algebra point of view, what this means is the very important fact that A belongs to GL2, the set of invertible matrices, if and only if the determinant of A is not 0. And A belongs to GL2 then if and only if A inverse exists. And that ends this particular video.